Hey everyone, just wanted to let you know that, I may be at Cedar Point when you're listening to this, or if you listen to it later, I won't be, but whatever. I may be at Cedar Point while you're listening to this in class, but considering what the weather was supposed to be like tomorrow or today, for that reason, whatever, I'm probably not going to be enjoying myself, just so you know, all right? But anyway, here, hopefully you guys have finished up your balancing equations quiz, and that quiz is over in the top tray, and I'll get that graded, and I'll have it back to you on Thursday when you come in for lab. So right now, you should have something to write with, and then there should be a new set of notes over on the red tray that's called Types of Chemical Reactions. It looks like a star, and it has a couple of pictures inside of it, so you should have a copy of that so we can get started. Today what we're going to work on is we're going to look at how we classify chemical reactions. What we'll find out here in just a second is that chemical reactions, which we have a general description of, and we'll talk about that general description, review that general description in just a second, chemical reactions follow certain patterns. And we see that even though we may have different reactants, different products, the patterns are very similar, and there's only a couple of them. So we're going to talk about those different types of patterns and why they fall into that. So first, we're going to start in a set of notes that we did way back in March, I think, the beginning of March, and that's changes in matter. You don't have this stuff on your note sheet, the star picture that I gave you, but hopefully you'll remember it. First, we talked about chemical changes, and we said that our definition of a chemical change is when one substance reacts with another substance and one or more new substances are formed. And we said in the last chapter that elements accomplish this through bonding. This is how chemical changes occur, that substances will form bonds with one another to create new substances that have different properties, right? And then you get into the whole trading of electrons versus sharing of electrons, et cetera, et cetera, et cetera. But really the bonding is how these things happen. And we also talked about that there are certain things we look for when we're looking for chemical changes, and that generally when a chemical change occurs, one or more of these things happens, but that doesn't necessarily mean when these things happen, a chemical change necessarily occurred. So the first thing we look for, right, color change. Okay, that's the first thing we look for. Second thing we look for, production of a gas, or bubbling, right? Third thing we look for, formation of a precipitate. So we get two solutions, and then we get a solid out of them. A lot of times that just means that it could be cloudy, but we still get some kind of a solid out of it. And then the fourth thing that we look for is generally energy given off in the form of heat or light. That those four things will generally indicate that a chemical change has occurred. I really don't probably have to do this, but I'm going to because you know how I am. So, right, there's one thing we look for, right, there's another thing that we look for, right. Like I said, probably don't have to do this, but I think you'll appreciate it when you watch it. And then, here we go, last one. So, chemical changes. Substances reacting with other substances through bonding to produce something new, something with different properties than we had before. And generally, we're looking for one or more of these four things to indicate that that has occurred. That takes us to today. Generally, all of those things apply to chemical changes. But what we find out is when we start analyzing them a little bit more closely, we see that patterns start developing, that there are certain ways that chemical changes occur, certain ways that elements are making new substances with new properties. So we're going to start off with a combustion reaction. A combustion reaction is a reaction that most of you are probably familiar with. A combustion reaction is basically fire. But by definition, a combustion reaction is an exothermic reaction where a substance, generally a hydrocarbon, but not always, combines with oxygen. So first, exothermic reaction means it's going to be giving off energy in the form of light or heat. And you can see on the screen, right, I have a picture of the Hindenburg, which gave off light and heat, unfortunately, and people got hurt and died, and that's not good. But generally, we say that a hydrocarbon combines with oxygen. Not always, but a lot of times. You can tell by its name probably that a hydrocarbon is a compound that contains both hydrogen and carbon. So if we take a look at an example of this, when a hydrocarbon combines with oxygen, we always get two products. If it's a good combustion reaction, if it's a good complete combustion reaction, we end up with two products, carbon dioxide and water, in addition to our light and heat. And I think and yesterday, if you did the balancing equations homework, I think you ended up with something that looked like this, right? There was a CH4 plus an O2, and that gave us CO2 plus H2O. And then to balance it, I think we threw a 2 here and a 2 here, and that makes it all balanced. But you see that this is a combustion reaction because one of our reactants is oxygen, O2. It has to be in the form of O2. Just because there's oxygen on the reactant side of the equation doesn't mean that it's a combustion reaction. A combustion reaction is when we have O2, oxygen gas, as one of our reactants. Now, when the other reactant is a hydrocarbon, like CH4, that's when we get the carbon dioxide and water. If oxygen is reacting with something else, we won't necessarily get carbon dioxide and water, but a good complete combustion reaction will produce this. This is where we get into, with the Bunsen burner, the difference between blue flame versus yellow flame. Blue flame is producing carbon dioxide and water, and that's it. Yellow flame is producing other stuff, and we won't get into too much detail there. But that's our definition of a combustion reaction. Okay? Next, synthesis reaction. Because most of you are familiar with the English language, you know what synthesis means. It means putting stuff together or making things. And that's generally what we talk about with a synthesis reaction as well. First, two or more substances react to form one product. So just like the picture is suggesting, we're taking simple things like pieces of a puzzle and putting them together to make something more complex, like the finished puzzle. One of the products that we form is larger and more complex than any of the reactants. A lot of times that will be element plus element forming compound, but it could be simple compound plus simple compound forms more complex compound. That's still a synthesis reaction. Examples of synthesis reactions. First, here's a process that is on the balancing equation sheet that I gave you yesterday, the formation of ammonia gas, which is this NH3 product over here. We call this the Haber process. Nitrogen gas, N2, plus hydrogen gas, H2, gives us NH3, ammonia gas. Don't worry about the G's that are there. Those are just indicating states of matter. That's something that you'll get into more complex when we get into chemistry. Here's one we've talked about a bunch of times, right? Producing water from hydrogen and oxygen gas. I think we've balanced this equation like 3 times now when you look at what we did in class and also the practice stuff that I gave you. But still, element plus element giving us a compound. Rust. Rust is a synthesis reaction. We're taking iron, combining it with oxygen gas, and producing Fe2O3, iron oxide. This is a synthesis reaction, but because one of the reactants is oxygen, this could also be classified as a combustion reaction, right? The products aren't carbon dioxide and water, but this has oxygen is one of the reactants, so technically it's a combustion reaction as well. Another example of a synthesis reaction. Generally, we look at patterns, look for coming up with ways to represent these patterns, so we're going to use some letters. When we look at a general form for a synthesis reaction, we're taking A plus B, two simple substances, and making something more complex, AB. They're joined together. They're chemically bonded. They've made a new substance with new properties. Example, copper plus oxygen gives us copper oxide. This is why the Statue of Liberty is green. The Statue of Liberty is actually made out of copper. When it was original form, it looked like a penny, but over time it reacts with the oxygen that's in the air, and it forms this other compound called copper oxide. Guess what color copper oxide is? It's green. That's why the Statue of Liberty is green. This also could be a combustion reaction, because if you look at one of our reactants, O2. Sodium plus chlorine gas gives us NaCl, sodium chloride. We showed this a couple of times in class with our YouTube clip. This is a synthesis reaction. We're taking two simple things and joining them together. If we go back to what we started with at the beginning, right? That reaction of sodium and chlorine definitely fits this category, right? Energy given off in the form of heat or light. If you remember what it looked like when we watched it on YouTube, it also making one or more new substances. So we're definitely seeing that these things are coming full circle, but we're starting to categorize them a little bit more.